Okay, as we continue 12.2, this is example 6. The unemployment rate rose rapidly after the 2008 recession before starting to decline, falling from 9.8% in 2010 to 4.9% in 2016. For these years, the unemployment rate can be approximated by this function they give us. X equal 10 corresponds to the year 2010. Find and interpret the point of inflection. Now, again, I left the picture. We just want to confirm what the picture actually says by doing the actual math part of it. So first thing we want to do to find the point of inflection would be to find the first and second derivative. So first derivative of this particular function, that gives us 0.135 x squared minus 3.51 x plus 21.6. Second derivative, let's see, 0.27x minus 3.51. So to find our point of inflection, we would let it equal to 0, but I'm going to look for when it's increasing, concave up, so I'm just going to put it in like we have here and see if it worked like it did last time. I'll do greater than 0. So let's see. X is greater than, I think this gives you 13. But you know what? I don't think that, oh, it is concave up. Yeah, you're right. It is. It's declining, so that's what messed me up there for a second, but it is. Okay, so our point of inflection is x of 13. And if I plug in 13 in my original formula, I believe you get this. Don't know why I put parentheses there. So our point of inflection is that. Now, this actually means in 2013 that it's 7.37%. Okay, so that's the meaning of those particular numbers in this particular circumstance. Now, on in the wording, it means the unemployment was decreasing at an increasing rate from 2010 to 2013, but then decreasing at a slower rate after 2013. I could put at a decreasing rate if I wanted to. Now, the next part talks about the law of diminishing returns in economics. It's actually related to the idea of concavity. This graph of this function kind of gives you an idea about it. Pretend that this, or not pretend, this is x representing your input, y is representing your output. So for instance, the input on this one might be advertising costs. Output could be the corresponding revenue from the sales. So you see that there's a point at which the more money you keep putting in, you're going to get a less of a return after. So notice the point of inflection on that. On the concave up portion of the graph, the output y is increasing at a faster rate with each dollar spent. However, the rate of change on the concave downward portion shows the increase in y is smaller with each additional dollar spent. So further input beyond C dollars, whatever that is, produces diminishing returns. So that point of inflection is called the point of diminishing returns. The rate of increase reaches its maximum at the point of diminishing returns. So any investment beyond the value C is not considered good use of capital. So that's hugely important if you have your own business or you're working in a business and you're in charge of making good decisions to keep this business profitable. So let's look at example 7. The revenue generated from airline passengers is related to the number of available seat miles, x, by that function. X is measured in hundreds of billions of miles, and R of X is in billions of dollars. Is there a point of diminishing returns for this function? If so, what is it? Seems to me there would be one. I mean, it just kind of makes sense, but we're going to check and see if it is. Okay, so first step, find our first derivative. And I've done these numbers, so you can double check them if you like for me. I know you guys are amazing at doing that. But I believe this is what it comes to for the first one. It's not one you can easily just kind of look at and write the answer, which would be nice. But at this level in math, the higher level you get, the more you have to, get wonderful, interesting numbers, shall we say. Okay, so our second derivative, I believe, is negative 5.568x plus 62.984. So our point of inflection would be where that is equal to 0. So let's solve it. Okay, I got about 11.31. That means they do have a point of inflection. There is a point where a point of diminishing returns, a point where you don't want to spend more than that. Or let's see what that is. If we actually plug in, say 11, because this is 11.31, right? If I plug in 11 into that second derivative, I believe I got 1.736. That's a positive number, so I know it's concave up right there. If I plug in 12, I got a negative 3.832. So that is concave down. Remember, you're just looking whether it's positive or negative in these cases. If I plug in this actual point in 11.31 into the original function, I get 133.54. So what this means is that the point of diminishing returns is 11.31 trillion seat miles. Sorry if I'm not writing too neat. I'm trying. Increasing seat capacity beyond this would not be financially feasible. So if you were working for this airline, you'd say, look, we don't want to invest any money past this particular thing, this particular amount of seats available. All right, so let's look at the next one. Okay, the next part goes into, well, no, let's see, that was example 7. Oh, all right. All right, let's see. Okay, example 8. Government consumption expenditures and gross investment in billions of dollars can be approximated for the years 2006 through 2016 by that function, where x equals 6 corresponds to 2006. Find all local extrema for this function. Interpret your answers. Okay, did I skip a piece of this page? I sure did. Okay, so let's look at that before we go into example 8. Notice here, and this is something I feel like we've talked about already. If a function f has a local maximum at c, the first derivative is defined, then the graph is concave down. If it has a local minimum at d, and then The first derivative at the D is defined. The graph is concave up near D. So the second derivative test is listed right here. If the second derivative is greater than 0, then that function has a local minimum at C. If the derivative is less than 0, then there's a local maximum. If it's equal to 0, then you don't really have any information from that. You can only use that first derivative test. So lots of little rules to remember here. So let's see how that works with our example 8. I know I just read it to you. I'm not going to read it to you again. First thing we're going to do is find the first and second derivatives and take a look and see what happens. Okay, so first derivative would be 8x squared minus 184x plus 1040. So that means our second derivative would be 16x minus 184. So our second derivative of, well no, first we have to find, if we want local extrema, we got to do first derivative. Let's see if I can factor that and make it equal to 0, right? Set that equal to 0 and solve. So that would give me 8. Well, factor out the 8 before I write it down. Does that factor? Oh yeah, it does. That would be x minus 10, x minus 13. Yeah, so x is 10, x is 13. All right, so what I need to do is find the second derivative value for these two values. These are my critical values, right? So find the first one. I'm going to plug it in over here. So second derivative of 10 would give me, let's see, that would give me negative 24. And then the second derivative of 13, that gives me 24. So this tells me that there's a local max at x equal 10 and a local min at x equal 13. So it's just another way of looking at that. Okay, so interpreting our answers, this means that government consumption and investment were at a local maximum in the year 2010 and a local minimum in 2013. So let me write that down. Government consumption and investments were at a local maximum. And if you actually plug it in, you get about 3,163 billion in 2010 and a local minimum, which if you plug it in, you get about 3,127 billion. Oh, I should have wrote that on another row. In 2013. So that's basically what it's meaning. And we have finished our notes for 12-2.